Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Dulong and Petit's law. Let's begin. Dulong and Petit's, two scientists, proposed their laws regarding the thermal properties of solids. Basically, how temperature is related to specific heats of that of solid. So, what is specific heat? Specific heat of a substance is the amount of heat required to raise the temperature of that of substance to 1 degree of 1 unit mass of that substance is known as specific of that of given substance. So, how in that of case specific heat is related to temperature. In case of solids, when some kind of heat is applied to that of solid, or we can apply some thermal energy to that of solid, the internal energy of that of solids increased. That increase in internal energy performs two activities. One is the atoms inside that of solids are vibrate their mean position, and the electrons present inside that of atom are thermally excited. Due to this, two energy sources are required for the increase of internal energy of that of solids. One is due to that lattice vibration and another one is due to that of electrical excitation. That electrical excitation is too small. We have only considered the energy due to that of lattice vibration. So, internal energy of that of solid is due to that of lattice vibration inside that of solid. So, now that lattice vibration is due to that individual atoms, and these individual atoms inside that of solid is just a harmonic oscillator. So, we have to derive let us derive an expression for the energy U of a three-dimensional linear harmonic oscillator, three-dimensional harmonic oscillator that having mass small m and angular frequency let omega. Therefore, the energy U is equal to, due to its kinetic energy plus potential energy, so U is equal to its kinetic energy, that is p square by 2m, plus its potential energy half m omega square r square. That is equation number 1, where p, that is the momentum, and r, that is the displacement from the mean position. and that is given as r square as x square plus y square plus z square in 3 dimension. Let we have to calculate the average energy. So, average energy can be calculated by taking Boltzmann's distribution law, applying Boltzmann's distribution law. The average energy of each harmonic oscillator is given by, so U average U bar is equal to, according to that of Boltzmann's distribution law, that is integration over U into e to the power minus U divided by kBt du whole divided by integration over e to the power minus U divided by kBt du, where kB Boltzmann's constant. Let us substitute the value of U in that of expression. So, we have du as in terms of momentum and position, the double integration for momentum p and position r, value of u is putted, that is p square by 2m plus half m omega square r square e to the power, value of u is putted, and simplifying it, e to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt, that is dp dr whole divided by, again double integration p and r, momentum and position, e to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt dp dr is equal to, separating these terms, that is multiplied to this term, that one is also multiplied by this term, and separating these two individual terms, integration over p and r, p square by 2m e to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt dp dr divided by the term double integration p and r to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt dp dr plus another term half m omega square r square double integration over p and r half m omega square r square e to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt into dp dr whole divided by again that term double integration p and r e to the power minus p square divided by 2m kBt into e to the power minus m omega square r square divided by 2 kBt into dp dr. Look that particular integration, double integration, integrating with respect to dp and integrating with respect to dr. Here also integrating with respect to dp and integrating with respect to dr. In that of numerator and denominator term, if we taking the integration with respect to dr in numerator and denominator term, integrating with respect to dr term is cancelled out, only dp term exists. Here we obtain only dp term, and that dp term integrating from the limit minus infinity to plus infinity, p square by 2m e to the power minus p square divided by 2m kBt dp divided by integration over minus infinity to plus infinity, only dp term exists. So e to the power minus p square divided by 2m kBt dp plus. In that scenario, here integration with respect to dp as cancelled out in numerator and denominator term, only integration with respect to dr exists. So that integration from the limit minus infinity to plus infinity, only dr term exists, that is m omega square r square divided by 2 into e to the power minus m omega square r square divided by 2 kBt dr divided by dr term exists as dp term in that of numerator to that of denominator term cancelled out, minus infinity to plus infinity e to the power minus m omega square r square divided by 2 kbt dr. Here we have to use some substitution as in place of we are taking it as equation number 2. Let we use the substitution as p square divided by 2m kbt is equal to a square and m omega square r square divided by 2 kbt is equal to b square, we assume. So that equation number 2 becomes, therefore we get u average is equal to for that term we use kbt a square, p square divided by 2m kbt is equal to a square. So instead of p square by 2m, it is a square into kbt. That integral term is equal to kbt integration over minus infinity to plus infinity a square e to the power minus a square dA whole divided by integration from minus infinity to plus infinity e to the power minus a square dA. Look at this. What is dP? If we differentiate that particular term, so we obtain a term having dA and a constant. Again, in that of denominator side, in place of dP we have a term some constant into dA as we differentiating that particular term. So in that of numerator side and denominator side, these constants are cancelled out. So only we have dA plus same thing. If you differentiate that term, we have dr with some constant, and again in place of that is dB with some constant as you differentiating that term. Again also for dr a constant with dB. In numerator and denominator term, these constants are cancelled out. Only the existing term as kbt integrating term minus infinity to plus infinity b square e to the power minus b square dB whole divided by integration over minus infinity to plus infinity e to the power minus b square dB. Another equation, equation number 3. We know the standard integration, we know from standard integration the integration over minus infinity to plus infinity a square e to the power minus a square dA is equal to root over of pi divided by 2 and integration over minus infinity to plus infinity e to the power minus a square dA is equal to under root of pi. These two standard integrals are used to evaluate that equation number 3. Now that equation number 3 can easily be evaluated. Therefore, u bar is equal to kBT root pi divided by 2 divided by root pi plus kBT root pi divided by 2 whole divided by root pi or u bar is equal to, that is 2 times of kBT root pi by 2 whole divided by root pi. So root pi cancel out, 2 cancel out. So u bar is equal to kBT. Let equation number 4. That is the average energy of each harmonic oscillator. But what will be the total vibrational energy of that of crystal? If that particular crystal has n identical harmonic oscillator, then the total energy will be n times into that of average energy. Therefore, the net vibrational energy of a crystal having a number of identical harmonic oscillators in 3 dimensions. In 3 dimensions is given by the total energy U is equal to 3 dimension. We use 3 at the degrees of freedom will be 3 into n identical harmonic oscillator n times of that of average energy U. Therefore, total energy U is equal to 3n kBT. Let we have to calculate what be the molar specific heat at constant volume. We know molar specific heat at constant volume is given by Cv is equal to dq by dt at constant volume, whereas V is equal to constant. In place of dq, that is du plus pdv divided by dt at constant volume. dq is equal to du plus bdv from first law of thermodynamics. that is equal to du by dt at V constant plus P dV by dt at V constant volume. So dV is equal to 0 here, that term cancelled out. Only the specific heat due to du by dt at constant volume. Let me put the value of du here. So d by dt 3n kBT is equal to 3n kb, n into kb, n into kb is equal to r, r that is universal gas constant, universal gas constant, and its value is equal to 8.31 joule mole inverse into Kelvin inverse. So finally we obtain Cv is equal to 3 R. Cv is equal to 3 R. That above statement is referred as Dulong and Petit's law, which states that the specific heat of solids, the specific heats of solids, of all solids at all temperature is constant, and that is equal to 3 R. That also indicates the specific heat is independent of temperature. The specific heat is independent of temperature and the nature of the solid, So according to Dulong and Petit's, the specific heat of all solids at all temperature is constant and is equal to 3 R. The specific heat is independent of temperature and nature of the solid. From that Dulong and Petit's law, we conclude a result as Dulong and Petit's law, Petit's is in arrangement, that is in an agreement with the experimental observations the experimental observations for many solids only at high temperatures. According to this law, at high temperature the specific heat of solid is independent of temperature. And that law also confirms that the specific heat is constant. Specific heat is constant, means Cv is equal to 3R, that does not depend upon temperature. At high temperature, the specific heat of solid is independent of temperature, but in low temperature, it does not hold good. That be the limitation that law. Low temperature it does not hold good, that one is the limitation of that of law. If we plot the graph between Cv and temperature that with the 3R. So, for lead that line for lead, that line for aluminum, that line for silicon, and that line for carbon or diamond. So, for diamond, that Dulong and Petit's law fails badly. So, with the help of this video lecture, you understand the concept of Dulong and Petit's law. First, we taken the average energy as kBT, next total energy, and by using that total energy concept, specific heat of that of solid, and it is shown that specific heat of that of solid is a constant and it does not depend upon that of temperature according to Dulong and Petit's. But his law holds good for high temperature and does not explain in low temperature. So, with this useful and informative notes, let me wind up this session. Thank you.